You have one long chocolate bar, and you may cut it exactly once. If you split it into a long piece and a short piece, where would you put the knife? Cut it right down the middle and the two pieces are identical, which is dull. Cut near the end and one side looks pitiful. So where along this bar is the cut that looks the most stable, the most beautiful? Remarkably, the answer to this almost childishly simple question has a name of its own. It is the golden ratio. Its symbol is the Greek letter phi. Its value is an irrational number that begins with 1.618. Here is today's journey. One cut becomes an irrational number, and that number is written into seeds and stars. The real starting point is this one fact. The cosine of 36 degrees is exactly half the golden ratio. Why should a single pentagon hold that whole irrational number? That answer is today's destination. Let me reassure you. The only tools you need are division and ratios. Everything else we will build as we go. We cut a single segment, and out of that one cut, the ratio called the most beautiful is born. The definition is one line. Divide it so that whole to long is the same as long to short. That sounds a little abstract, so let us take a bar and first cut it right down the middle. Whole to long is 2 and long to short is 1. The two ratios do not match. Now the opposite. Let us slide the cut near the end, stretching the long piece out to 0.9. This time we get 1.111 and 9. The gap is far wider than before. The middle is too small, the end is too large. Somewhere in between, the two ratios meet exactly. Right here. The spot where the long piece is 0.618, and the short piece is 0.382. Divide the whole by the long piece, or the long piece by the short piece, and both give 1.618. The whole is 1, the long piece is x, the short piece is y. And 1 over x equals x over y. The name given to that common ratio is the Greek letter phi, what we call the golden ratio. Its value starts at 1.618 and runs on forever after the decimal point, an irrational number. Read the other way around, the long piece is 1 over phi, and the short piece is 1 over phi squared. But why is this cut so special? A single rectangle shows us the answer. From a rectangle whose sides are phi to 1, we slice off a single square. What is left is phi to 1 all over again. The real magic of the golden ratio lies in this self-similarity. Now let us dig that value out by hand. The golden ratio was the whole divided by the longer part. Call the longer part 50 and the shorter part s. Then phi splits into 1 plus s over L. But s over L is simply L over s turned upside down. It's reciprocal. So one clean line is left. Phi equals 1 plus 1 over phi. This one line is the heart of the golden ratio. The definition has itself sitting inside it. Multiply both sides by phi to clear the fraction, and the denominator vanishes completely. What is left is an ordinary quadratic equation, the kind you met in middle school. We plug the coefficients straight into the quadratic formula. Under the radical, 1 plus 4, which is 5. So the answer is 1 plus or minus the square root of 5 all over 2. Two of them come out. We are dealing with a ratio of length, so we throw the negative one away. The positive one that survives is exactly that value. This equation lays bare the character of the golden ratio. Let us line up 3 bars side by side. Add 1 to phi and you get its square. Subtract 1 and you get its reciprocal. The digits after the decimal point stay the same. It is a strange number, one where adding and subtracting stand in for squaring and inverting. We can see the same story in a picture. Let us overlay one parabola and one straight line. Y equals x squared and y equals x plus 1. Where the two curves meet, the two expressions are equal. There are two intersections. The right one is the golden ratio, 1.618. The left one is psi, negative 0.618. One step further. Take the square root of the squared equation, then feed phi back into the right side endlessly. Do the same to that one line at its heart, pour phi into itself forever, and a continued fraction grows. Do these two infinite expressions really meet at the same place? The more layers we stack, the tighter they cling to the gold dashed line. The nested radical climbs steadily from below, while the continued fraction closes in, swinging above and below. In the continued fraction, the denominators are all 1, the smallest number there is. That is exactly why it is the hardest to approximate. One quadratic equation, two infinite expressions, and the same number every time. That stubbornness is what leads to the sunflower in the next chapter. The golden ratio does not stay on paper. It shows its face all over the world around us. The Parthenon of ancient Greece, and the spiral of a seashell. People love to call these the golden ratio. But there is a catch here. The moment you actually put a ruler to it, the story changes. The value shifts depending on where you decide the edge is, so it never lands exactly on 1.618. So the modern verdict is that a good many of these stories are romantic readings fitted on after the fact. But do not be disappointed yet. There is a place where it really is written in with no sleight of hand. It is not length, it is angle. Let's divide one full turn 360 degrees by the golden ratio. The larger piece is about 222.5 degrees. The angle left over is about 137.5 degrees. That leftover angle is called the golden angle. It is the angle at which a plant sends out its leaves, one after another. Why would a plant pick this angle of all angles? Remember, the golden ratio is the number fraction's approximate worst. What if the leaves turn by a rational fraction of a full turn, like 1/2 or 2/5? After only a few leaves it overlaps an earlier one exactly, and they shade each other. No sunlight reaches the leaves below. Turn by the angle that fraction's approximate worst, the golden angle, and the leaves never overlap. So they share sunlight in space as evenly as anything can. Now let's check it with our own eyes. Seeds placed at the golden angle leave no gap in any direction. By contrast, at the rational angle of 144 degrees, the seeds line up into 5 spokes and leave wide gaps. The worse an angle is approximated by rationals, the more efficiently nature uses its space. The golden ratio also turns up in a sequence. 1 1 2 3 5 8 13, the Fibonacci sequence. Take the ratio of 2 consecutive terms and keep going, and in the limit it converges to the golden ratio. The proof has its own episode on Fibonacci. Now we head for the shape where the golden ratio hides most elegantly. Now for today's real star. The shape where the golden ratio hides most elegantly, and most exactly. The regular pentagon. Draw every diagonal joining the 5 vertices, and a 5-pointed star, a pentagram, appears. Let's start with the angles. The formula for one interior angle of an n-sided polygon looks like this. Put 5 in place of n, and you get 180 times 3 divided by 5. That comes out to 108 degrees. But the 2 diagonals drawn from one vertex slice that 108 degrees into 3 equal pieces. So the apex angle of the sharpest triangle is 36 degrees. That angle is the key to today's story. To turn that key, we need one thing first: the exact value of cosine 36 degrees. A calculator only tells you 0.809, but what it really is exactly half the golden ratio. Line the 3 values up side by side, and they match perfectly out to 10 decimal places. Here's the derivation briefly. If theta is 36 degrees, then 3 theta is 108 degrees and 2 theta is 72 degrees. Plug in the triple angle and double angle formulas, set C equal to cosine theta, and the cubic splits into a product. C is not -1, so the quadratic on the right gives the answer. Feel free to just take the conclusion and move on. Path 1. With that value in hand, let's pull out the triangle we shaded red earlier and look at it alone. Set the base to 1 and call the 2 legs we want to know x. Our weapon is the law of cosines. Substitute the value of cosine 36 degrees and clean it up, and x squared is left standing alone. Now rationalize the denominator. Multiply top and bottom by 3 plus the square root of 5, and the denominator becomes a clean 4. But there's a radical inside the radical, and there's a formula for peeling off this nested radical. Set a to 1 and b to 5. Then 6 is 1 plus 5, and even 2 times the square root of 5 fits exactly. So x is 1 plus the square root of 5 over 2. The very golden ratio we've been chasing all along. In a regular pentagon, the ratio of diagonal to side was the golden ratio all along. What's more, only 2 kinds of pieces fill that star, and both are isosceles triangles. So whichever of the 2 you pick, the legs and the base are in the golden ratio. The small pentagon formed inside holds another star, and that star holds an even smaller pentagon. The scale factor is 1 over 5 squared, 0.382, and on top of that, it turns by 36 degrees every time. Here comes the second path. We can reach the same conclusion far more simply with no messy cosine computation at all. Let the whole be 1, the long piece x, and the short piece y, then write down the definition of the golden section exactly as it stands. But y was 1 minus x. Put the two together and 1 minus x becomes x squared. Divide both sides by x squared and set t equal to 1 over x. Then t squared is t plus 1. The very equation we met in part 2 has popped out again, this time from inside the regular pentagon. The last one, the third path, brings a more grown-up weapon, Ptolemy's theorem. In a cyclic quadrilateral, the sum of the products of the two pairs of opposite sides always equals the product of the two diagonals. The pentagon's 5 vertices all lie on one circle, so apply the theorem directly to quadrilateral ABD. Divide both sides by s squared, and for the third time the very same equation jumps out. The law of cosines, the ratio of segments Ptolemy, all 3 paths gather into one and the same equation. Leonardo da Vinci drew the polyhedra for Pacialize the divine proportion, and their faces were exactly this pentagon. This is the final chapter. From a single cut to a star, how did the story travel all this way? This looked like a general tour of the golden ratio, but the real starting point was one very small fact. That the cosine of 36 degrees is half the golden ratio. That single gear tooth was everything. That gear tooth caught the law of cosines, the proportion of segments and Ptolemy's theorem, and turned them all. The 3 paths started from different places, but at the end they met in one and the same equation. Let's retrace the road we walked. We set out from one question. Where do you cut a chocolate bar? The condition on that cut became the irrational golden ratio, and that number was carved into nature as the sunflower's angle. A story that began with a single division passed through an irrational number, infinite expressions and a star and came back to this one line. Let's go back to that very first cut. A chain where an idea becomes a formula, and the formula becomes a picture again. The closer your fingertip comes to 0.618, the more this entire story fits inside that one single cut. If you enjoyed today's video, please subscribe, hit like, and turn on notifications. See you in the next story.